Hey Jordan, did you get a chance to look at that paper I sent over, the Misaligned by Design one?
Oh yeah, I did. The one about incentive failures in machine learning. It was a really interesting read. I mean, it tackles a problem that seems so straightforward on the surface.
Totally. The core idea is about these high-stakes situations, where getting something wrong isn't just a simple mistake.
Right, like their main example, medical diagnosis. Misdiagnosing pneumonia when it's not there is an inconvenience, sure, but failing to spot it when it is there, that can be life-threatening. The cost of the two errors is completely different.
Exactly. And that brings us to what everyone currently does, which is the whole point of the paper. The standard practice is to just tell the AI about this. You train it with what they call a utility-weighted, or asymmetric loss function.
It makes perfect sense, intuitively. You basically program the model's priorities. You tell it, hey, a false negative for pneumonia is 99 times worse than a false positive, so I'm going to penalize you 99 times more if you miss one.
Yeah, you bake the human objective right into the training process. The paper gives it a name, which I thought was helpful, the Aligned Learning Premise, or ALP, the fundamental belief that if you train the model on your objective, it will get better at your objective.
It seems so obvious, it's almost silly to question it. Of course that would work.
And that's the punchline. The entire paper is about how that seemingly obvious premise can be completely wrong. It can actually backfire.
Wait, backfire how?
Get this. Training the model with that weighted loss function can make its performance worse. And not just worse in some abstract sense. Worse when measured by the very same weighted objective you were trying to optimize for in the first place.
No way. How is that even possible? You're telling me that by explicitly telling the AI, this is what I care about, you make it worse at achieving the thing you care about? That feels like a paradox.
It totally does. But their proposed solution is what really clarifies it. It's almost elegant in its simplicity.
Okay, I'm listening. What's the magic trick?
It's a two-step process. First, you train the machine learning model with a completely standard, normal, unweighted loss function. You don't tell it anything about the asymmetric costs. Its only goal is to become as accurate as possible at predicting the true, underlying probabilities of each outcome.
So you're just building the best possible probability engine first. The goal is for it to learn to say, based on this X-ray, there is a 7.3% chance of pneumonia, a 92.1% chance of nothing, and a 0.6% chance of something else. Just the raw facts.
Precisely. You completely separate the learning part from the decision-making part. Then comes step 2. After the model is fully trained, and you have this super accurate probability machine, you apply the human objective as a simple rule on top of it. They call it an ex-post adjustment.
So that's when you bring in the pneumonia is super important logic. You'd create a rule that says something like, okay, model, even if you only think there's a 3% chance of pneumonia, that's high enough for us. Flag it. You just change the decision threshold at the end.
You got it? And this is where their economic model comes in. They argue that machine learning isn't one single task. It's two distinct, incentivized tasks. The first task is learning how to classify. That's building the accurate probability engine. The second task is choosing how to classify. That's making the final call based on those probabilities.
And the standard method, the ALP, conflates those two. It tries to do both at once, and in doing so, it screws up the more important, learning part. This new method keeps them separate, letting each part do what it does best.
Exactly. The weighted training correctly incentivizes the choosing part, but it poisons the well for the learning part.
Okay, that makes conceptual sense. But did it actually work in practice? It's a nice theory, but the real world of deep learning can be messy.
That's the most convincing part of the paper. They tested it on two very different, very standard applications. The first was the pneumonia diagnosis from chest X-rays, using a deep neural network, just like in a real-world scenario.
And the second one?
Image classification on the CIFAR benchmark dataset, which is a classic task, but they used a modern transformer model. So they covered both a real-world medical problem and a standard computer vision benchmark, with different state-of-the-art architectures.
And the results?
Their two-step method, train unweighted, then adjust, consistently outperformed the standard method of training with a weighted loss. And again, this is when measuring performance using the weighted objective itself.
Consistently? Like, a little bit better?
No, significantly better. For the pneumonia task, their method resulted in a weighted loss that was nearly 7% lower on average. That's a huge improvement. And they have this one graph, figure 1, in the paper, that is just damning. It shows the weighted loss over the course of training for both methods. The blue line, their method, is just strictly below the red line, the standard method, at every single training epoch.
Wow! So it's not just that the final model is better. The entire learning process is more efficient and effective from start to finish. It's just, a better way to learn.
Yes, it's completely dominant. It's not just a fluke or a lucky final result. The model is just learning better, period.
That's wild. So, if I'm understanding this right, the most effective way to make an AI system align with your complex, real-world priorities is to hide those priorities from it while it's learning? It feels so counterintuitive.
Right? It's like trying to teach a kid to be a good baseball batter by telling them to only swing for home runs. You might get a few, but you'll mess up their fundamental ability to just see the ball and make good contact. It's better to teach them the fundamentals of hitting first, and then talk about strategy later.
That's a great analogy. So the big, overarching conclusion here is that the aligned learning premise is often false. Just because an objective seems right for the final decision doesn't mean it's the right objective for the training process.
Exactly. And the reason why it fails is the key insight. When you put a huge weight on one class, like pneumonia, you're correctly incentivizing the model's final choice. It becomes very cautious and will flag anything that even remotely looks like pneumonia.
But that must be what messes up the learning. How, though?
The paper says it flattens the learning landscape. I think the intuition is this. If the model knows it's going to have to classify something as pneumonia for any probability above, say, 3%, it loses the incentive to get really good at distinguishing between a 5% probability and a 25% probability. In both cases, the final action is the same, so why bother learning the subtle features that differentiate them? The gradient that pushes it to learn those nuances gets weaker.
Oh, I see. It learns a coarse, blunt strategy, because that's all it needs to satisfy the weighted objective. It stops refining its understanding of the world, because the objective doesn't reward that refinement anymore. The value of new information goes down.
You've nailed it. The very thing you do to align its choices inadvertently misaligns its incentive to learn.
This has huge implications for AI alignment in general. Everyone is so focused on how we can specify human values perfectly so the AI can learn them. This paper says that even if you have a perfect description of your values, embedding it directly into the training objective might be the wrong move.
For sure. It suggests that alignment isn't just a problem of defining the destination. It's also a problem of designing the right journey. You need to provide the right incentives for the model to actually acquire a rich, accurate representation of the world first.
Otherwise, you end up with a system that's doing what you told it to, but in a dumb way that's ultimately worse for you. It's misaligned by design.
There's the title. Man, what a thought-provoking paper. Really changed how I think about setting up these problems.
Same here. It's one of those simple ideas that just clicks and makes you see the field a little differently. Anyway, I've got to jump on a call.
Cool. Great talking it through with you. Thanks.
You too. Catch you later.